Okay, here's the final part of the 2019 Oxford PAT. We're on question 21. You wish to build an adjustable delay line using electrical switches as shown in the diagram below. Okay, so each one of these can toggle up and down. So we're either taking a quick path at the bottom or a slow path at the top by the look of it. So his purpose is to adjust the delay of an electrical signal through the delay line by switching different amounts of delay. Yeah, delay line should use a minimum amount of switches. Should have a minimal delay L min and a maximal delay L max is less than or equal to L min plus delta L. Right, we refer to delta L as the delay range. Right, so that's what we can push it up to if we were taking the top path. So L max is top path all the way, L min is bottom path all the way. Delay should be adjustable in increments of dL so that the line can achieve an evenly spaced set of delays between L min and L max. Right, so we've got our L min, our L max, and then we've got all of these need to be equally spaced all the way through with resolution between each one of this delta L. For all segments in the line, you have to determine a common small delay L, which is active when the switch is in the lower position. And how many segments? We've got N segments, right? Right, that's fine. You further have to determine a larger individual delay for each segment. Okay. The line with N segments satisfy the demands on the minimum number of switches, minimum delay L min, delay range DL, and right, so yeah, this is our delay range, top to bottom. That's our delta L. That's our L max. That's our L min. Right, so this is all fine so far, which means find a value of L in terms of L min and N. Right, well, N lots of L is our L min. Yeah, because N times L, that's if every, because we've got N segments. So the minimum we can do is N lots of short path, which will be our minimum value. So L is going to be equal to L min divided by N. Right, let's hope it's all like that. Find the delays of each segment Li in terms of delta L. Right, that seems a lot more fiddly. Each segment Li in terms of delta L. Right, so we need to go, let's just have a think again about this, what I was laying out. So we've got our L min, we've got our L max, we've got a number of steps in between the two of them, and each one of these is this delta L, and we need a minimum number of switches in order to hit these. So every permutation of switch, if we're going to optimize this for a minimum number of switches, every permutation must take us to one of these. So yeah, every permutation is equal to some, is like an L min plus a, I don't know, some kind of multiple of A times delta L, whatever that is, you know. So yeah, and we have to hit each one of them uniquely. Right, so we can't have duplication in this. So what if we had, let's think of a simple setup then. I'm trying to get the idea of this duplication. So say we had 3 switches, and so that means we've got, if we've got 3 switches, that means we're going to have 8 permutations. I mean, we're going to have 2 to the 3 permutations. So we could have all of them off, that is L min. We could have all of them on, that is L max. But then we've got another 6 permutations. Actually, this fits, I've drawn 8 lines here, so that's handy. So that's going to be our 0, 0, 0. That's going to be our 1, 1, 1. Oh yeah, this is pushing me into binary counting here, isn't it? So we need to hit each one of these lines with a different combination of switches as we go along. So if we've got, So one of them's going to have to just have a delay of this delta L in order to go up one step. So we need, if that one was delaying by delta L and we did that one on, off and off, then we'll go to L min plus delta L, which is going to be here. So that's good. Then we need to go up 2 delta L's. So if we do 2 delta L for that one, then we'd have 0, 1, 0 would be plus 2 delta L. Then for 3, we can have those. For 4, we'll have that one. Yeah, we're just binary counting. So 4 delta L. What do we want? So the delays for each segment. So we're going for up to I. So if that was 1, 2, 3. So what are we doing here? So we're saying that 1, 2, 3. This is I equals up to I. We're getting that Li is equal to delta L, 2 delta L, 4 delta L. What will be next? Then we'd have, so 4 would go to 8. Oh yeah, so we're taking 1 off the number and doing the power of that, aren't we? 2 to the power of I minus 1 multiplied by delta L. So, oh, is that what I want? Li, yeah. So Li is equal to 2 to the power of I minus 1 times delta L. Because it doesn't matter what order you put the switches in. We can have these in any order. So these I's are sort of interchangeable. Yeah, we could wire them up 2, 1, 3 or whatever order we want. It doesn't matter. Find the minimum necessary N. Minimum necessary N. Right, I'm not sure what that in minimum necessary N in terms of delta L and DL. Big delta L and little delta L. Right, so big delta L, that is our difference between these things, L min and L max, which is going to be, is the sum of all of these big L's, is the sum of Li. And we're going up to N. So N equals 1 to N. I mean, I equals 1 to N. So that is equal to, so we've got, let's factorize that delta L. 1 plus 2 plus 4 plus 8 plus up to 2 to the N minus 1. So what does that sum up to? So we've got N terms. We're doing sum to N. A is 1. R is 2, so we want 2 to the N minus 1 over 2 minus 1, which is 2 to the N minus 1, multiplied by DL. So delta L is equal to little delta L multiplied by 2N minus 1. That's right, isn't it? And what do we want to do on this? Oh, we want to solve for N, was it? Fine, yeah, we need to solve for N. Right, so we've got that 2 to the N is equal to big delta L over little delta L plus 1. So we just need to log on both sides. So N is going to be equal to log base 2, big delta L over little delta L plus 1. That seems a little bit of a concern. So what if, just wondering, because N we want to be an integer, and that isn't necessarily going to give an integer. So what do we know about delay resolution delta L? L max is less than or equal to L min plus delta L, because we haven't used anything about this. What is that going to mean then? So L max is less than or equal to delta L. So we worked out delta L is that, oh, it's just saying it might not sit on the line. That's what it is, isn't it? That's what it's saying. That we might have, these might be, like our L max might be inside the last delta L. So we're just inside it. It can't go beyond it. So L max is then, yeah, less than or equal to L min plus delta L. Right, okay. So we could have that if it doesn't divide into it exactly, because this is going to give an integer. If, actually, well, we don't know, it might not though, might it? Particularly as delta L, but it's not even just that, because unless we've got a power of 2 in here, we've got some weird value for n. So it's going to have to be, so it's not just the case of the last one might be short. It might be that we're in that next block of powers of 2 and L max is short. But we've got to round up. We're going to have to, because if it's not, if L max is inside the last one, then we still need to include it. Yeah, we might end up, if we're solving this, we might have only got up to here. We would have done enough in order to get all of our delta L's in. And so, oh, well, we need a fraction of the next one in order to get to L max. But of course, we can't have a fraction one. You have to go up to the one which is beyond it. So we're going to have to round up our n value. Because, yeah, we're doing all of these. This is our counting up that we need. This is counting up our n's. Well, sort of. It's going up in blocks, though, isn't it? So it's not, we're not counting up individually. Every time we add on a new, yeah, if we've got one switch, then we got one option. When you add in the second one, we're then saying, well, we've now got four permutations. So we start off with 2 permutations, that's right. Then we go to, because we've got on and off. Then we've got our 4 permutations. Then we've got our 8 permutations. I've drawn 9 lines. So every time we add in a switch, that's n is 1, that's n is 2, that's n is 3. So every time we add in a switch, we get an extra load of lines. And so they come in these blocks then. So we've got the 2, we've got the 4, then we've got the 8. So if we've got our L max was sitting, say, here, that's our L max. Well, we can't say, oh yeah, well, we just do a bit of it. We just do a fraction of adding a switch in. You have to do a whole switch to get up to the next bit, which adds in all of the delta L's in order to cover that L max. Yes, I've talked myself into it now. I can see where that's coming from. So yeah, you have to round up. Hopefully that makes sense. If you think of the number of permutations you're adding on every time you add a new switch, because we're adding a whole new column onto our binary number, an extra digit. It's like if we're thinking in base 10 of saying we're going, you know, from 1s to 10s to hundreds to thousands. So each time you move up with an extra digit, we're adding in a whole big chunk of stuff. And we need to make sure, well, we have to have all of that into the possibility of increasing our delay time, even if our L max is inside it. So we've got to round up to include all values. That was a horrible question because they really haven't made it that clear what they're getting at. Whereas really, they just want you to be able to count in binary numbers, but they haven't made that clear at all in what they're after. I think if they'd set it out a bit more clearly, then that would have been easier. So if you've struggled with this question, as I have done, then don't feel bad about that. I think this is a bit of an anomaly. And yeah, if you can't do this, don't in any way let it knock your confidence, because it's a very difficult question worded in a way that makes it even more difficult. So hopefully the rest of the paper will be a bit friendlier than that. Okay, onwards, and let's hoping for better luck on this. 22. Conical cup has dimensions shown in the diagram below. Cup can hold a maximum volume of V when filled to full depth H. Okay, find an expression for depth H, little h. You have to fill the cup so it contains half the volume. Well, that's a bit easy, isn't it? So if you halve the volume, because, well, that means we just have to cube root the factor, because we're scaling by length is going to be a cube root of the change in the volume. So we'll have to be that H is going to be capital H over the cube root of 2. Well, there's not really much more to say about that. That's just scale factoring, isn't it? Yeah, we want to have something which is that bit smaller, which has now got H. It doesn't matter what D is, because D has to be in proportion to H. So, yeah, I don't really know what to say about that. That's just 4 marks they've handed over. Maybe it's compensation for the previous question, because that question 21 was a nightmare. Question 23, in an imaginary water filtration process, a fraction 1 over n of an impurity is removed in the first pass through a system, and then you get the same thing going all the way through. Show that if n is 2, the water can be made pure, n is 3, then it won't. Right, so we're just setting up, right, so if n equals 2, we're going to get a half, then we're going to get a quarter, then we're going to get an eighth, then we're going to get a 16th. This is what you're removing each time. Removed each time. So we want to do sum to infinity is going to be a half over 1 minus a half, which equals 1, i.e. all removed. And then we're going to want to do that again for n is 3, so it'll be a third, a ninth, etc., etc. Sum to infinity is going to be a third over 1 minus a third, which is a third, divided by 2/3, which is a half, i.e. half removed. Right, okay. Yeah, it's easier to think about it being removed rather than what's left, because you're then adding up what's taken away each time rather than trying to work out how much you've got remaining. I know the two things are more or less the same thing, it's just different sides of the same coin, but you can add up what's removed much easier than, well, you can't add up what's remaining because that's not what you're doing, you're just trying to calculate what's remaining. But if you add up what's being removed, then this becomes trivial. So that's that bit. I think this brings us to the last one, I think. Yeah, question 24. So we've had 2 easy ones after a difficult one. This doesn't look as though it's going to be easy, though. We've got a sketch below, shows a ball of mass m on a spring, unextended length r0, spring constant k. Spring is pivoted on the left on a central axis marked with a cross. Right, that's this bit, yeah. Axis is perpendicular to the plane of the sketch. The ball and spring rotate around the central axis on a smooth horizontal table. All right, so we're looking down on something. So this is just going round and round in a circle with the spring at the middle, and the spring is providing the centripetal force. The spring will break if it's stretched with a force larger than F max. Find the equilibrium extension R. There seems to be a clash here. Of the system when it rotates with angular frequency omega. So that isn't R, that's R. What was it? Unextended length R0. So we've got R0 plus R is what that is if the extension is R. So we need to get the equilibrium extension R of the system when it rotates with angular frequency omega. Right, so we're just doing an F equals MA. So M, well, R omega squared. Right, let's not get these R's mixed. So this is the radius of our circular motion is R0 plus R. So that's MR in inverted commas omega squared, and that has got to be equal to the K times R, which is the extension. Right, what do we want? So we need to find, well, just solve this for R. So R is going to be equal to, well, we got M R0 omega squared, that's our constant there, and then we're going to have to divide by K minus M omega squared. Right, so that wasn't so bad for starters for 3 marks. Maybe this question isn't going to be as bad as I thought. Let's not count chickens. Find the equilibrium angular frequency omega c at which the spring will break. Right, let's just copy this thing down because we might need to use this. So we add R is M R0 omega squared over K minus M omega squared. Are we going to have to use this? So we've got find the equilibrium angular frequency omega c at which the spring will break. They told us something about that before, didn't they? F max. So F max is going to be equal to K times R max. So that is going to be, and that is at this critical. So that's at omega c. This we can just put in then. So that's going to be K times all of this thing. So M R0 omega c squared divided by K minus M omega c squared. Fine, and now we've got to rearrange it for rearrange it for omega c. Right, that means we've got F max times K minus M omega c squared is equal to Km R0 omega c squared. Oh, how annoying. So what have we got left with? We got a K times F max. That's going to be what's left on the left hand side, and then we're going to have to divide by, we want the omega c squared on that side, so we've got to divide by a KMR0 and then a MF max. Actually, let's just do the square root now. So get rid of that squared, put the square root in KF max over KMR0 plus MF max. Right. Okay, fiddly rather than anything else. That seemed a lot for 1 mark. Sketch omega c against F max in the range from 0 to 1 Newton. Right, so what are all our bits here? We've got 0 to 1 newtons. We're doing omega c versus F max. We've got M is 1, R0 is 1, K is 1. Okay. Right, that shouldn't be too bad, I wouldn't have thought. So we only need to worry about positives on these. So that is F max. We're going from 0 to 1. This is our omega c. So what is our formula with all of these things in then? Omega c will be equal to, so K is 1, so we've got F max on the top. This is all under the square root. Over 1 times 1 times 1 is 1, plus 1 times F max. Okay, so we've got to do a square root graph, so that's something that looks like that. It's got to go through, we're going from 0, which would be 0, so it's going through there, up to 1, so 1 over root 2 here. So that's root 2 over 2. And it's going to be, so we haven't got to the, any kind of, yeah, it's just going up in a root graph, so a bit of a curve on it. Okay, that's good. That was part C. Label your axes. Yeah, right, I've done. What have we got now? Under some conditions, the system can only achieve a maximum angular frequency omega I less than omega c. Find a relationship between Km and omega I. Explain what happens to the system as the angular frequency increases to omega I. Explain what happens to the system as the angular frequency increases to omega I. Right, okay, so we've got some angular frequency. So, right, so what happens then? So as it gets quicker and quicker, so we start off with this, if it starts off at rest, so we want to find a relationship between Km and omega I. Km and omega I. Km omega I. And explain what happens. So when omega is 0, we're just at rest on the table. At rest on table. So as omega increases, then we need R will increase to provide the centripetal force. To maintain, I suppose, to maintain circular motion. What happens then? What did it just up to as it approaches, or as it increases to omega I? So when we get to omega I, well, that's all that's going to happen. That's going to be the limit of it staying in a circular motion. The trouble you're going to have with it is when you get past that, we're going to have some value of R, aren't we, where this is going to break down. How are we going to get this relationship between R's going to not be able, so when, I mean, it hasn't asked for this, but when it gets above this value, what we're saying is R can no longer, increase in R can no longer provide necessary centripetal force. I know it hasn't actually asked for this bit. I'm quite surprised it hasn't asked for what would happen after. So circular motion stops. It will spiral out. Circular motion becomes spiraling outwards, which is what it's doing anyway. Spiraling outwards. Oh, but yeah, it can't stop it. It has no stable. Yeah, I suppose this is the thing. If you've got some value of omega which is fixed, it will be stable for a fixed omega. Stable for fixed omega. The trouble is now if you keep even for fixed omega, if you keep a fixed omega which is above this critical, well, it's not the critical is when it was snapped, but this omega I, if you go above that, it's not going to be stable. It's going to be spiraling outwards, trying to find a force that will provide the centripetal, well, make the circular motion possible, but it won't be able to find it. So we need some breakdown in R. We had a relationship for R that we wrote down somewhere. Here we go. So, right, okay, we can see it. So mr0 omega squared over k. Right, so let's repeat that again. So this is r omega, oh no, it was r0 omega squared, wasn't it? Got to go back to it. mr0 omega squared k minus m omega squared over k minus m omega squared. So we can see what's going wrong here now, because you need to be able to have a real value of R. So R, so this is from A, this is from part A, what we worked out. R must be real and positive. So this means that we need to have k minus m omega squared needs to be greater than 0. So we're going to have that omega squared needs to be less than k over m. So our omega I is going to be equal to the square root of k over m. Yes. So yeah, so that's saying if you've got a spring that isn't stiff enough, that's got a low k, then there's only so much circular motion you can contain, as in it will fail in its ability to maintain circular motion before it snaps. So a stiff spring will be able to maintain the circular motion until we get, so it'll keep on increasing, it will keep on moving out further and further. As we increase omega, we're going to keep on increasing R as omega goes up. That's fine. We can see that's going on here. As omega goes up, our numerator is going up, our denominator is going down. So we're moving further and further out, but and it's still maintaining the stable circular motion until eventually the spring snaps. If you've got a weaker spring with a lower K, okay, as you increase omega, it's going to move out further and further. But the thing that's going to fail is the ability to provide stable circular motion. It's going to get to a point where it just can't provide that force anymore. And that means that stable circular motion will stop and it will just keep spiraling outwards. So you'll still be going round and round in circles, but even if you're not increasing omega, R will keep on increasing, and then eventually it will snap. It's not that it won't snap, it's the fact that it will snap once circular motion has failed. It's going to just keep on, R's just going to keep on going out further and further and further, and then your spring's going to go. So that's the difference between these two types of spring then. One of the springs can maintain stable circular motion all the way out to the snapping point. The other springs won't. They maintain stable circular motion up to a point, and then they just give up, start spiraling outwards. You're getting some kind of, well, I don't really know what to describe it as. Yeah, that's another very difficult question. I think this has been quite a tough year this year. There's been some very easy questions like the last couple, but they're very wordy. There's a lot to take in very new situations where they're giving you a lot of new information, a lot to read, which is going to put a lot of time pressure on this paper. A lot of time pressure. So I think this is quite a difficult one. It's had some horrible questions. This one has been tough. You had that really annoying one with the switches. There was another one as well that was fairly horrible. So I think this has been a tough year, and it's a different style of paper. So if you're prepping for PATs and you're looking at the earlier papers, which had a lot less to read, then yeah, maybe the more recent papers I think are going to help more. There's a lot of understanding to try and deal with, a lot of ambiguity as well. I mean, it hasn't helped that they've put so many typos in this paper as well, and haven't explained questions as well as they could have done. But I think this is a different type of difficulty where you don't have as much time to think. Yeah, this has been a tough year, I think. But anyway, that's brought us to the end of another paper. And yeah, moving on to the 2020s on the next one. So I will see you for that.